In this lecture, we'll talk about dependent samples t-tests for mean difference. These are sometimes called paired sample test or matched sample test. If we have the ability to do so, it is best to, quote, match observations from one sample with observations from another sample before testing. This is usually possible in the following scenarios. If you're doing a before and after assessment of subjects with an intervention between, that might be something like a training program where students are measured for their ability to do something like type, and then they're measured after a training program. We would compare each of the subjects' times in terms of how fast they type from before they did the training to after they did the training. In this case, we would have two samples of data. Those two samples would be the before and after, but they wouldn't be completely independent of one another. They would come from the same group of people, so they would be dependent samples. Another scenario in which dependent samples are used is in the medical studies. In medical studies, it's impossible generally to give someone a disease twice so you can test them with a placebo and then test them with a drug. Instead, what a medical study will attempt to do is find a number of individuals that match other individuals given certain traits, such as age, race, gender, maybe BMI, body mass index. If we match people based on such things like that, then the two people may not be the same person, but they're very similar people, and now we can give one of them a drug and one of them a placebo. In this way, we can create two samples that are very much dependent on one another, and I'll show you how to do the hypothesis test to find differences between the two samples. As an example, after a weight loss program, we may wonder if subjects have actually lost weight on average. In this case, we would likely measure the subjects before and after the weight loss program. So we would have two samples of information, however, they would be very dependent on one another. A medical field study may be one where, say, 150 people are taking a drug for clogged arteries. Their arteries were measured for flow rate. Another 150 people were matched one by one to the first 150 people by traits such as initial artery blockage, age, gender, race, and level of physical activity. This second matched sample was given placebos. Is there evidence that the drug reduces artery blockage? You can see how the two samples are very much dependent on one another. We've linked them based on a number of similar traits. Now what we can do is focus on the difference between the drug and the placebo. Here's an example problem. 8 subjects participated in a weight loss study. Their weights were measured at the beginning of April, before the weight loss program, and at the beginning of May, once the program was completed. Is there sufficient evidence at the 5% level of significance to suggest that the subjects lost weight on average? Check out the hypotheses here. What we're really focusing on is the difference in each subject's weight between May and April. So we call that the mean difference, or mu sub d. If the mean difference in this case is negative, is less than 0, that indicates that the average weight has decreased over the time of the training program. In step 2, as we typically do, we gather the data. Here, Freddie M. lost 3 pounds from April to May. Stevie N. lost 5 pounds from April to May. Pete T. lost a pound. Pat B. gained a pound. Don H. lost 4 pounds. Cindy L. stayed the same. Donald F. lost 3 pounds. And Diana R. lost 2 pounds. Notice how I've indicated the differences in a third column. Negative differences imply that the weight went down, which would be a good thing. Positive differences indicate that weight went up, which would indicate that the weight loss program was not working very well. We're going to focus our test on this sample of differences here, rather than 2 independent samples of April and May. In this way, we're treating them as dependent samples. We summarize the information in this third column so we can do the hypothesis test. X bar D is the average of the differences. So X bar D, or your book might refer to it as D bar, is negative 2.125. I encourage you to check that on your own to make sure you can calculate the average as well. The standard deviation of the differences, or SD, is 2.031. There are 8 observations, so n is 8, and thus the degrees of freedom will be equal to 7. In our critical valued approach, we need to find a test statistic and a critical value. Here we'll be using a t-distribution again for our test statistic. The test statistic you may recognize. It's calculated in the exact same way we calculated for t-tests for one sample means tests. We take the difference of the sample mean and the hypothesis mean, and we divide by the ratio of the standard deviation over the square root of n. Here are the numbers from the problem. The observed weight loss on average, 0, which represents the hypothesized weight loss if no change was made, and then the ratio of the sample standard deviation to the square root of the sample size. Be sure to calculate the same test statistic that I did at negative 2.96. The critical value in this case for a 5% level test will come from the 5% one-tailed column of your t-chart in the 7th row for 7 degrees of freedom. Find the number 1.895 to be sure you know where that comes from. In step 4, we make a decision about the null hypothesis based on our test statistic and critical value. The test statistic of negative 2.96 is farther from 0 than is the critical value of 1.895, and thus we reject the null hypothesis. We would say there is sufficient evidence at the 5% level of significance to suggest that the subjects lost weight on average and that the weight loss program worked to some degree. Let's move on to bonus coverage of this type of hypothesis testing. We ask ourselves, what if the researcher already assumed they would lose weight and wanted to show sufficient evidence that they had lost more than 1 pound on average? Before, we were just seeing if they lost any weight. In other words, if they lost more than 0 pounds. Now we want to know, did they lose more than 1 pound? Notice how the hypotheses change. We hypothesize as a researcher that the weight difference will be less than negative 1 on average, indicating a greater than 1 pound decline in average weights. If you recalculate the test statistic, you'll get negative 1.57, and you will be unable to reject the null hypothesis because that is closer to 0 than is the critical value of 1.895. Another what if. What if we had accidentally done a 2-sample t-test from section 9.2, treating the April and May weights as independent samples? If you punch that into your calculator, you'll find that the test statistic is very, very close to 0, indicating no statistical significance at all, and we cannot reject the null hypothesis. In this scenario, we would be unable to reject the null hypothesis, and we would come to the conclusion that the weight training program didn't work. But we just saw when we ran the appropriate test that the weight training program did work. Thus, this method likely led to a type 2 error, being unable to reject a false null hypothesis. If the null hypothesis is false, in other words, if the weight training works, we'd like our test to say that. The first test that I showed you did say that. In other words, it was correct. The second test here committed a type 2 error, and it was all because we used the wrong test. Using a dependent samples testing method, as we did in the first case, we can reduce our chances of a type 2 error. That's the advantage of matching data sets. Let's do another example problem. Consider the medical example at the top of the lecture. 150 patients received a drug to reduce artery blockage, and 150 matched subjects received a placebo. These matched subjects were matched based on traits such as age, gender, race, and initial artery blockage to make sure that the pairs were all very similar to each other. We would hope that the only difference between each pair is that one receives a drug and one receives a placebo. In this particular study, the drug group outperformed the placebo group by an average of 5% blockage removal, with a standard deviation of 15%. Is there sufficient evidence at the 5% level of significance to claim that the drug worked? Generally, when we're doing these matched studies tests, the null hypothesis includes a value of 0. We're comparing against a difference of 0. That's because a difference of 0 indicates no change, and typically our null hypothesis indicates no change. So here we allow the equality to be found in the null hypothesis. The mean difference could be equal to or less than 0%. As a researcher, we'd like to show that the drug has more artery blockage removal than the placebo group. In steps 2 and 3, we're going to gather data and perform the critical value method. Here we have an average difference, a d-bar, of 5% additional blockage removed from the drug group than the placebo group, and we can convert that into a decimal as 0.05. The standard deviation was reported to be 15%, or 0.15, and the sample size would have been 150 matched pairs. Thus, the degrees of freedom is 149. The test statistic, as you'll recall, is calculated by looking at the difference of the mean and the hypothesized mean over the sample standard deviation divided by the square root of the sample size. You should calculate a test statistic of 4.08. Try it for yourself. The textbook doesn't have a row for exactly 149 degrees of freedom in the t-chart. So you'll have to go round down to the 100th row, 100 degrees of freedom, with a 5% one-tailed test. You should find a critical value of 1.66. Your calculator will find a critical value for you for exactly 149 degrees of freedom. On your TI-84, go into the second VAERS button, scroll down to INV-T. It's the inverse of the t-distribution, which gives critical values of the t-distribution. You want to enter 0.95, the 95th percentile of the t-distribution is also the 5% one-tailed column from your book, with 149 degrees of freedom. There you see a critical value of exactly 1.655. Pretty close to what the book said, but a little bit more exact. Now when we make our decision, we see that the test statistic of 4.08 is farther from 0 than is the critical value of about 1.66. Thus we reject H0 and conclude that there is sufficient evidence at the 5% level of significance to claim that the average percent of blockage removed is greater for the drug group. In other words, there is enough statistical evidence to suggest that the drug works. Let's do this test on the calculator. I'll show you a cool way to enter data and complete a test like this, letting the calculator do the work for you. Go to your Stat button, and the very first option is to edit your lists. Go ahead and click that. Here I have called up lists 2, 3, and 4, L2, L3, and L4. Your calculator will likely have an L1, L2, and L3, but whatever it has, it doesn't matter. You can use whatever lists are there. Notice I have entered the data just like I would in an Excel file for April in list 2, for May in list 3, but like I said, I want to calculate the differences. I don't really care what the April data was or what the May data was. What I care about is how much each person changed, how much weight each person lost. I could come over here and enter the 8 differences. I could do it in my head. It's not hard. But if you had a really long list, that would kind of suck. I'm going to show you how to make list 4, in my case, or whatever your third list is, do a math equation on the first 2 lists. In other words, I want it to subtract list 2 from list 3. Go up to the column of the list. Notice I've selected L4. Press Enter. And now you're going to tell it to do list 3 minus list 2. So I go second 3, and I get L3, minus second 2, and I get L2. Notice that list 4 automatically fills in all of the math, does all of the subtraction for you as you told it to. Now we'll perform a t-test, a one-sample t-test for means, on list 4. So I go to Stat, Tests, just a simple t-test. I want to enter from data. This is the first time I think we've ever entered from data, so I click enter there. My null hypothesis is 0. My list is in list 4. You can get there by clicking second 4. Always leave the frequency at 1. And now we want to see if the weight loss, or if weight lost, is more negative than 0. Remember, our test was a lower-tailed test. Now we calculate. You should recognize that test statistic, negative 2.96. That tells us that we were lost weight, and that we lost weight by quite a bit on average. The p-value is 0.011 if you round to the nearest third decimal place, the nearest thousandth. A p-value that's less than 5% is grounds for rejecting the null hypothesis, and we come to the same conclusion that we did in the first test. That's how you do a dependent samples test on the calculator when you have to enter from data. If you're doing a dependent samples test on the calculator and you already have the statistics, then you just enter it like you did for a one-sample t-test for means.